Okay, two things before going back to falling balls. The first is that I have now finally put up the first problem set, which goes through the first chapter of the textbook. Will include ramps, which is still in our future. It's 20 questions, multiple choice. Hopefully most of them are pretty straightforward. No calculations, all conceptual. It's on Wiley Plus, the textbook website. You should be able to see it from the home page when you go into the class. Also, I think the modules, you may have a modules page that has it as well. It's 20 questions. You can come and go from the problem set as many times as you like. When you submit a question, it'll tell you whether you're right or wrong. You get a second chance for half credit. So it's not, you can't keep guessing, don't guess. Try to know what the answer is before you do it. There's a button that was supposed to go away, but it's still there. The button says send a gradebook. It's a nuisance. You can press it more than once. You can press it and don't worry about it. If you press it, and you may have to navigate back to the problem set, but just keep on picking off the questions until you've answered all 20, and then press it. I don't know why it hasn't gone away. They claimed it would. Any questions about the problem set? Other than it's due a week from today at class time. So 1 o'clock, not midnight. It's in class time. If you don't get it done in time, you can take the whole set for half credit for the rest of for another week, and then it's no longer valuable. All right, so that was item one. Item two is I'm in the process of moving all my whole bunch of websites out of the university and into the cloud because UVA doesn't really like to have websites that are world accessible and that it does not control. It's just very risk averse and controlling. So anyway, I have moved the website for the class out onto the web. It should redirect you. I haven't put all the redirections in gory detail, but you should end up on the new site. It's 10. Oh, I guess I can write it out. 1060 at Bloomfield Web. .com. So, oh well, things change. The only complication, well, there's always a complication, but if you want to look at the old exams, I don't really want to let those be world accessible openly. So it'll ask you for a username and password to look at an old exam, and the username and password. The username is Virginia, no capitalization, and the password is physics, no capitalization. So now that's on the video as well. So people out in the world who are watching this video can go in there too. But I just don't want them spread all over the world, all those questions. Okay? So that's the story of websites. And that then brings us back to looking at physics and looking at how things fall. And I'll remind you that a falling object, by my definition, the falling object is an object that's experiencing only one force, its weight, which is equivalent to saying it's experiencing the downward force due to the Earth's gravity. But that's the wordy version of the same thing. All right? At this point, we'll leave air out of the story. In fact, for this semester, we'll pretty much leave the air out of the story. It does mess up things somewhat because you get air resistance issues. But if we neglect air, things can experience only one force, namely gravity. And so let me ask you one of these clicker questions associated with this. There it is. So if you hold the ball still and then drop it, so as it's falling, as it's dropped, which of those 5 choices is the right, properly describes what it's doing, its motion? All right? And you can talk about this among yourselves. I hope you'll get it. The vast majority will find the right answer here. We'll finish up on the minute, 60 seconds. Okay, 3, 2, 1, 0, click, and dun-dun-dun. The correct answer is B, but there's some representation of the other answers. So let's look at them for a second here. So I'll get rid of this thing. So B is the right answer. The velocity increases steadily in the downward direction. So whatever the velocity was now, it changes a little bit, it changes a little bit, it changes a little bit. The changes are the same each unit of time, each second, for example. And that's equivalent to saying that its acceleration, which is the change of velocity with time, is constant, is steady. It's accelerating uniformly the whole time. So that's what B is telling us, or another way of saying B. How about A? Velocity becomes constant in the downward direction. This is maybe a perception that you have if you just are thinking about dropping something, and that as soon as you let go, it just snaps to some downward speed and then holds it steady. But you know that's not true if I won't actually have one of you do it. If I go over to one of you and say, I'm going to drop the ball like this, no problem, right? Of course, I can't even catch the damn thing. All right. On the other hand, if I drop it from the catwalk on your hand, no. So you know instinctively there's a difference between the ball hitting you having fallen a short distance versus falling a great distance. It's going faster. So A isn't the right answer because the velocity is not constant. It does not jump to some speed and maintain it. So far, okay? C. The acceleration increases steadily downward direction. This is going too far in the changes of the changes of the changes. The acceleration is constant. As we'll see, it's caused by the force due to gravity, namely the weight of the object. And that downward force, the weight, directly causes an acceleration. And since the weight is constant and the ball's mass is constant, being a character of the ball itself that can't change in any context, constant force divided by a constant mass, well, that Newton's second law says that gives you a constant acceleration. So the acceleration is not changing with time. There is such thing, there is physicists apparently do measure, I say apparently because I've never used it, the rate at which acceleration is changing with time. That's a really obscure concept. I mean, it's there, okay, fine, but I think it has the name jerk. So it's the J-E-R-K. Somebody used it, stuck with it. But we won't ever deal with it. I never deal with it. So the acceleration does not increase steadily in the downward direction. C is out. You're okay with that? D, the velocity and acceleration are both constant in the downward direction. And this was a popular one. Well, that can't be true for an interesting reason, namely that acceleration is the change of velocity with time. So if acceleration is anything other than zero, then velocity is changing with time. And it can't be a constant. The one case in which you can have acceleration and velocity be zero simultaneously is when the thing is not moving at all and not even trying. So the ball right now, its velocity is zero, okay, it's constant, and its acceleration is zero, constant. In the context of a falling object, you'll never get that. Acceleration's always not zero, and therefore velocity is changing with time. All right? The last choice, which was not very popular, position shifts steadily downward as the time passes. No, it does not come down like on an elevator. That would be the mid section portion of an elevator ride is typically pretty steady. And that's motion at constant velocity, not constant acceleration. So the ball is not shifting downward steadily with time. It's actually covering more and more distance with every passing second of fall. So it's speeding up, and therefore barreling ahead faster and faster, covering more distance. All right? Next question here. Did I put it up there? Yeah, it's up there. Okay, asking another one. A baseball weighs 3 times as much as a golf ball. If you drop them side by side from rest, which is to say they started motionless, which will fall faster and hit the ground first? You okay with the question? Go for it. This is basically where we ended up on Friday, a million years ago. We'll go to 30 seconds because almost everybody's weighed in here. 3, 2, 1, 0, clickety. Okay, the vast majority are going for they're falling together. A few of you are going for A, the baseball will come down first. And that's a reasonable thing to expect. It's not true, but it seems right because the baseball weighs more. In fact, this is a remarkable result. You know, this is one that sort of caught the attention of scientists for centuries. That if I take 2 balls, I don't happen at this point to have a golf ball, but okay. So I got a baseball and a bouncy ball. These 2 balls are different in mass, different in weight. What else about it? That's good enough. If I drop them simultaneously, they go down exactly together. They don't bounce the same, but they go down exactly together. That's strange. And so let me try to convey to you why it's strange and why this was so interesting to scientists. The baseball, when I let go of it, it accelerates downward in response to its weight, because of its weight, caused by its weight. So it's got a certain weight, and whatever that weight is, it accelerates in proportion to that weight. It also has a certain mass, which is, I think of as the resistance to acceleration. So the weight is yanking down on the ball, its mass is saying, no, 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 let's not accelerate. And the two battle it out, and you get a certain acceleration. And that certain acceleration is the weight divided by the mass. Yes, weight divided by the mass. The weight is the net force on the ball, so that's the cause. The mass is the resistance to acceleration, that's 1 over in the relationship. And the acceleration is just that ratio of its weight to its mass. Okay? And it goes down like that, okay? Which I guess, let me make sure I animate that a little bit so you can follow it. When I let go of it, so I'll go real slow. It starts at rest, and pretend my hand isn't here. And it's going very slowly at first, because it is accelerating downward, but it hasn't had much time to pick up speed yet. So it's still just barely moving. And then it goes a little faster downward, and a little faster, and a little faster, and a little faster, and a little faster, and it starts to really cook on its way down. So that's what's happening. It just goes quick. We can video it and play it back slowly, and you would see approximately what I just described. Okay, so this guy accelerates. Its acceleration is equal to its weight divided by its mass. All right, how about this guy? This guy, well, when I let go of it, and the only force acting on it is its weight, that's going to cause acceleration. And the acceleration that it experiences is going to be its weight divided by its mass. Well, they go down together. And what that tells us is the weight of one of these balls divided by the mass of one of these balls is always the same thing. It's a constant, and it's given a name. It's got a strange name, and the name is the acceleration due to gravity. So how fast does this guy accelerate when I let go of it? When it's falling, the acceleration due to gravity. And for those of you who've done physics before, it's approximately, it's not a constant of nature or anything. It is approximately 9.8 meters per second squared. Why the second squared? Because acceleration is the rate at which velocity is changing, and velocity is the rate at which position is changing. They're 2 time we're 2 per seconds away from being somewhere. So there's per second squared. In common American units, it's 32 feet per second squared. So what these mean is that if I start with a ball at rest and let it fall for 1 second, during that 1 second, it will have accumulated 9.8 meters per second of downward velocity, or 32 feet per second of downward velocity. That's what that kind of acceleration means. So let me go back to the notion that each of these balls, the ratio of their weights to their masses are the same as observed by equal accelerations. In fact, everything in this room does that. If we dropped everything around, again, neglecting air, everything would come down at 9.8, would accelerate downward at 9.8 meters per second squared. So why is that so remarkable? It's because what that says is that whatever the object's mass is, it develops a weight here that is equal to 9.8 SI units of force per SI unit of mass. That if you, the SI unit of mass, and I haven't paid a lot of attention to mass, to units. The SI unit of mass, the way in which you characterize how hard it is to shake something, equivalently, the amount of inertia the thing has, it's the kilogram. There are other ways of talking about mass in the SI system that are factors of 10 different. For example, the gram is 1/1000th of a kilogram. And the metric ton is 1,000 kilograms. All right, so anyway, the kilogram is the good unit of mass. The SI, or metric unit of force, is the Newton, named after Sir Isaac, of course. And the Newton is a little push. It's not a big push. It's about the push, conveniently enough, that a small apple will exert on your hand if you hold it. It's about the weight of a small apple. Okay, so that's a Newton. It's about 1/5 of a pound, 1/4 of a pound. A pound is also a unit of force. It's just our unit, the American unit of force. Anyhow, going back to the balls and this observation that everything falls together, it says that it says that every kilogram of mass here near the surface of the Earth develops about 9.8 newtons of weight. That's just the way it is. This is true here near the surface of the Earth. If we go out into deep space, it's different. It's almost nothing. If we go to the moon, it's about 1.6 newtons per kilogram. But anyway, it depends on, gravity is not truly constant everywhere. It's pretty steady here near the surface of the Earth. So we sort of say, well, let's not worry about the fact that it's slightly, depends slightly on how far away you are from the center of the Earth. We can just sweep that under the rug, and in fact, we'll do that for the rest of this semester. And just say it's just uniform everywhere. Every object, for every kilogram of mass in any object, it will develop 9.8 newtons of weight. That's the way it is. And so therefore, if this ball has twice the mass of this ball, the baseball also has twice the weight of the little ball. So as the mass of the ball goes up, and we can go hog wild and go for a bowling ball, as the mass goes up, which by itself would slow down acceleration. The weight goes up, which by itself would speed up acceleration. And they go up by the same factor, and voila, everything gets the same ratio of the force on it divided by its mass. And everything therefore accelerates downward the same way. You all right with that so far? And you guys have been great asking questions. Please do. You can still use the gadget to send me messages. It's just going to be off this website. Otherwise, it should look identical. It's on the messaging system is on the front page of that website. Anyhow, why is this so interesting to physicists? It's because mass is an inertia thing. It has nothing to do with gravity. And yet, weight, which has nothing to do with inertia, it's all about gravity. This inertia thing mass, and this gravity thing, weight, they go together. I mean, who ordered that? Why did that happen? It's kind of a remarkable result. We'll see fairly soon that some things develop forces that had nothing to do with their mass. For example, if you got static electricity on you, and somebody else has static electricity on them, you're going to push and pull on each other. And the amount to which you push or pull has nothing to do with your mass. It's got to do with how much electric charge you've got on you. And so here's gravity worrying about objects' masses. And as the little aside, just brief one, is that this puzzlement, like why does gravity have anything to do with mass, ultimately led to the general theory of relativity, Einstein's revelation in the first part of the last century that, oh my gosh, what if we really look deeply at mass and weight and acceleration and tie them all together? And if you do tie them all together, then you get all this interesting so-called modern physics that you see show up from time to time in, say, science fiction movies, sometimes represented adequately, sometimes just hooey. But anyway, so it's one of these profound things about the universe that mass and weight do go together in these contexts. Okay, but having said that then, okay, so everything falls together. There are exceptions, or seemingly exceptions to that. I go just for fun and games here. Do I have something? If I drop, just to clue you all in on this, because the point of this class is to give you something of value. If I drop a sheet of paper, of course, it does not keep up with a ball, right? Ball wins, okay? So what's the problem there? Well, the problem, of course, is air resistance. And in the presence of air resistance, you get these weird things like the paper actually hits a final speed beyond which it doesn't go much faster, which is given a name that you're somewhat familiar with. It's called terminal velocity. If you drop something and consider the air, as it goes down faster and faster through the air, the falling object, it feels an upward breeze, and it starts to experience upward air resistance. And this could be you if you jumped out of a plane with a parachute. And the upward air resistance gets stronger and stronger as you go faster and faster, and there comes a point where that upward air resistance, which is a force on you, if it's you falling out of the skydiving, that upward force begins to cancel your weight. In fact, ultimately, it does cancel your weight. At that point, you stop accelerating. And so instead of coming down, going faster and faster, you actually come down steadily. And that steady speed is called your terminal velocity. It's a steady downward speed. And everything has a terminal velocity in our air, in our atmosphere. And so things come down at different speeds, depending on how they catch the air. All right? But the moment, again, I'm setting aside air resistance and just letting things fall. Like, how do I set aside air resistance for this? Well, I can let it draft. Drafting, like in bicycle races or running races, you can go behind the other person and run in a little air pocket behind them. And that cuts your air resistance. So if I put this sheet of paper on top of this notebook, they're not glued together, they're not stuck together by some air effect, but rather the book will get the air out of the way for the sheet of paper to fall properly. So the fancy physicist's demonstration of what I just did is to get the air out of the place by using vacuum systems. Okay, nah, too much trouble. So just get the air out of the way by just having something massive go ahead of it, massive and therefore heavy, go ahead of the object, the paper, and get the air out of the way so the paper could fall. The paper just fell, that's all it did. It wasn't sucked down by something. All right? Okay, I think I've done justice to that part of gravity. What else do I want to do next? Okay. Let me ask this question for you. It's up there. See what you think on this one. So you drop your cell phone and from some high balcony at a fancy hotel or whatever, and it's got 2 seconds before it smashes on the ground. Uh-oh. You are super fast, though. You're like what out of the kid out of The Incredibles. You can run really fast. Okay, down you go. You grab it, the cell phone, where it was after 1 second. So halfway to the ground in time. Where was it in space? What fraction of the distance to the ground had the cell phone traveled in half the time of the fall? You okay with the question? Questions about the question? I hope you understand the distinction between the halfway point in space and the halfway point in time. Just for added incentive, this is right out of some of my exams. So when you look at the old exams, you'll see this kind of question everywhere. We'll go to the 45-second point. You guys are good, actually. Most of you have this right. 3, 2, 1, 0. A it is. Yes, C, 3/4. This may be how you're interpreting a wording issue in the question, whether you're measuring a quarter from the top or a quarter from the bottom. But let me just, I'll just discuss it anyway. You may all have gotten it right. Or the idea is this: that when you drop that cell phone, or well, I guess it fell. You didn't do it on purpose. Why would you? It starts motionless, and it picks up downward velocity steadily. It's accelerating downward at a constant rate. So it's going faster and faster and faster and faster. During that period, then, it's covering more and more distance with every increment of time. So during the first few increments of time, it barely covers any distance because it was barely moving. So actually, in fact, that first second, it didn't make much progress. It's a 2-second fall, but during that first second, it started the second motionless, and it finished that second having picked up 9.8 meters per second of downward velocity. That's the consequence of accelerating steadily at 9.8 meters per second squared downward. The consequence is, in 1 second, you pick up 9.8 meters per second. So its speed in that first second was between 0 at the start and 9.8. I wish it were just 10. Maybe I'll just say 10. And 10 meters per second at the end of the second. So its average speed during that first second was fortunately halfway between those two. It's the average of those two. 0 and 10 is 5. Its average speed during the first second was 5 meters per second. Remember, a meter is about this, okay? So that was its average speed. And so in the first second, it traveled 5 meters. Because that's what happens if you travel at an average downward velocity of 5 meters per second. You manage to cover 5 meters in a second. How about the second second? The second second, the cell phone started already heading down at 10 meters per second. So it's got a huge leg up on the first second. So it's traveling down at 10 meters per second, and it finished the second traveling another 10 meters per second downward, which is 20. So it started at 10, ended at 20 meters per second. Its average was 15. So in the second second, it traveled 15 meters. So the first meter, hopefully this verbal math is tough. I realize this kind of stuff, it's in the book. It's probably, yeah. If it doesn't make sense, ask me about it. But the key thing is that in the first second, it travels only 5 meters. In the second second, it travels 3 times that far, having picked up so much more speed. So that's why when you go looking for that cell phone to grab it after 1 second, look high. It didn't fall very far yet. Is that okay? Practical applications for this. If you go out and you decide you want to make an amusement park, and you're going to have the longest bungee jump in history, right? So your competitors have 2-second bungee jumps or drop towers. The drop tower is the same idea. So let me just stick with the drop tower because it's more conventional for an amusement park. So the drop tower is King's Dominion. Those of you who've gone there, that's got a drop tower, and it drops you for about 2 seconds. And during a 2-second fall, you're exactly like the cell phone which we just determined traveled 5 meters the first second, 15, 20 meters grand total. So a 2-second fall takes you down about 20 meters, which is about 60 some odd feet, 64. Okay? How about a 3-second drop tower? Well, in that 3rd second of falling, if we dropped the cell phone so it could fall 3 seconds, look how fast it was going to go into during that 3rd second. It starts at 20 meters per second, the end of my previous story. It finishes at 30 meters per second. It goes an average of 25 meters per second. It's going to fall 25 meters in that 3rd second. And it's going to only get worse as you go longer and longer falls. So it turns out that a drop tower, 2 seconds is about right, because personally it's about all I can tolerate, 2 seconds of that feeling of falling. And 2 seconds is about all the height they can deal with. If they want to make a 5-second drop tower or a 10-second drop tower, now you need a skyscraper, because you're going to cover so much distance during the last couple of seconds. Is that okay? So, that kind of stuff shows up all over the amusement park. Drop tower is the extreme case, but some of these things, if you're accelerating, you can't keep the acceleration up in the same direction for very long. You go too fast, and it gets hard to work with. Yeah?
Is it a constant, like, for 3 seconds? If in the first second would you go 1/16th of the distance?
Is a constant in this that if you had 3 seconds, in the first second you would go 1/16th of the distance. You can calculate it, but it's not going to go, it's not a straightforward progression. In 3 seconds, we just determined that the 3rd second you would average 25 meters. So you go from 5 meters in the first second, 15, and then 25. That's a grand total of 45 meters, and you only went 5. So that's a 1/9. It's probably going to go like that. It's probably going to go like a quarter, a 1/9, which is 1 over 2 squared, 1 over 3 squared. It's probably 1 over 4 squared next, 1 over 5 squared. That's the sequence. I'm guessing it, but it's probably right. Okay? My main thing is that you realize that falling, you cover more and more distance with each second. That affects a lot of things. Like it's very hard to make a long fall, fall long in time because you cover too much distance. That's one observation. I've already done that one. What other ones? Well, that you're going faster and faster, of course, after you fall like that. So if you're diving, for example, those of you who've ever gone into the water, fallen into the water. If you fall into the water where you're so close to the water that it only takes 1/10 of a second to get there, you don't hit very hard because you're not traveling very fast. But those of you who have jumped off of cliffs or something like that, one time in camp when I was 13, everybody had to do it. And I wasn't going to dive. I would step off the cliff into the water, but I wasn't going to go head first. And we were probably, was it 20 meters or something like that? I mean, it was like the 2-second fall, which isn't very long, but man, do you hit hard. 2 seconds, for those of you who've done this, you probably remember, like, oh my gosh, it's like hitting cement. Hurt my ankle doing it. Once in a lifetime was enough for that one. All right, so if you go from 100 meters, it's going to be a problem. All right. Let me turn this off. Finish the stories of falling. So that gives you the idea of falling from rest. How about falling from traveling up? Which again seems sort of counterintuitive. Like, what does it mean to be falling but going up? Well, according to my definition of falling, which I think is the right one, a falling object is an object experiencing only its weight. We didn't say anything about which way it's moving. So if I've got the ball going up, it's still a falling ball, even on its way up, which is to say it's still experiencing its weight. It's accelerating downward at 10 meters per second. Everything's true about it. The difference is only in where it's located and, well, how its velocity what its velocity is and where it's located. What it's doing is it's going up. It's decelerating. Remember that term, which is just a specific term to say accelerating opposite its velocity. Its velocity is up. some amount that I gave it by throwing it. But its acceleration is down, the same as usual. The acceleration due to gravity, 9.8 meters per second squared. So how that manifests itself for the ball is the ball slows down. And it slows down all the way until it reaches peak height, at which point it's got no speed left at all. And it continues right through that moment of motionless and becomes a falling object from rest. From that moment when it was motionless, it's as though someone were up there and dropped it. And its motion is the same as that afterwards. All right? So objects that are going up can fall. It's not a problem. And I'll ask you another one of these guys. We're doing okay with them. All right, so here's one. So you can be a falling object. Don't always have to, well, here you're going to hit the water again, too. Suppose you're on a springboard at the aquatics, AFC, and you've bounced up and down, and it flings you up. Up you go, and we're going to have you go straight up, despite the fact that that means that you might encounter the board on the way down. We'll pretend that the board got whisked out of the way. So you went straight up, and then you come back down. At the peak of your jump, the highest moment in that rising, you're basically you're the ball going up and down. Okay, it's just a glorified story version of it. What's your velocity and what's your acceleration? You okay with the question? Give it a shot. The majority do not have the correct answer. So talk about this among yourselves. Nothing is touching you. The only force acting on you is gravity. You happen to be at the peak of your jump. What's your velocity? What's your acceleration? All right, I'm going to call it, and then I'm going to talk about stuff, and I'm going to ask you to do this one again. What should I show you? I'll show you the answers here. We're messy here, okay? Acceleration is the change of velocity with time. So if you're accelerating, your velocity cannot be constant. Is that okay, everybody? I'll show my hand. My hands are going to show you acceleration. My velocity is constant. I'm not accelerating. Now I'm going to accelerate. My velocity changed with time, and now I stop accelerating. And now I'll accelerate again. If I go to keep accelerating, I got to stop the story because I'm out of room. But acceleration literally is the change of time, change of velocity with time. Okay? Try this one again. This is better. Some people just running away from the answer they chose before because it was the majority. I'll give you another 10 seconds, and then we'll call it again. 5, 4, 3, 2, 1, 0. Oh, it's still all over the place a little bit. Now I'll let you do it. Let you discuss it, and I'll show you your choices. We can see whether the herd mentality works here. Although that of course will obscure the choice. There we go. Ooh, it fits. What causes acceleration? What causes the ball's acceleration? Its weight. Is its weight changing? No. Is its acceleration changing? No. That should kill off C and D. C and D are out because the acceleration is constant for a falling object. It's caused by weight, and their weight doesn't change for all practical purposes. It's constant. So C and D are gone. Okay, if your acceleration is constant, which it is, can your velocity be constant? Or is that a contradiction in terms? With the exception of, if your acceleration is 0, yeah, you can have a velocity of 0. But if your acceleration is anything other than 0, your velocity is changing. So get B out of there. No B's, no B. Yeah. Come on. Okay, good. A few of you are holdouts or are left. Ha. Okay, good. E is always the right answer. Special case. Okay, stop. All right, it's A. That when a ball is falling, and it actually, when the ball is falling, it doesn't even matter whether it's at the peak, right? Any situation when the ball is falling, its velocity, its acceleration is constant. It's the acceleration due to gravity caused by the weight, resisted by mass. And that means its velocity is changing. It doesn't matter. The whole time the ball's in the air going up and down, the velocity is changing. It's changing because it's the acceleration. All right? Just an add note to that. It's also a common misconception I encounter is that at the moment the ball's at the peak height, we actually start to put numbers on it, that somehow, well, that its velocity is 0. And that is true. The ball is neither rising nor falling at that moment of peak height. The misconception is that somehow its velocity is 0 and its acceleration is 0. No, not the acceleration is 0. The acceleration is caused by weight. And that can't change. That acceleration can't change. It's going to be downward. So what's going on at the moment of peak height? At the very top of the ball's height, if we zoom back a little and roll back the video, we take a video of it, go back a little earlier than peak height, you'll see the ball was going up because it was on its way to peak height. And if you roll the video a little ahead, a little past peak height, you'll discover, oh, the ball was heading down. So it was sweeping through the process of going up moments before to going down moments after. It's right at the 0, right where the velocity goes to 0. So if you want to, and I think I found people appreciate the graph. If I graph velocity, so this is time, and velocity, if I'm above the horizontal axis, that means it's heading up. If I'm below the horizontal axis, that means it's heading down. The velocity, as you throw the ball up, is, of course, it's upward initially. And right at peak height, it hits 0. And after peak height, it's heading downward. And right at peak height, that's the moment of peak height. It will never go any higher than that because it's no longer heading up. And then moments from now, it'll be heading down. And the slope of that curve, actually, which is the rate at which velocity is changing with time, is the acceleration. It's downward. Anyhow, as the ball hits peak height, its velocity is momentarily 0. Really, truly the moment. Don't measure it over any length of time. It's not 0 now. But it's continuing to accelerate downward, just like any other falling object. All right? So that's the trip up, the trip down. 2 cents about the trip up. Because it slows down as it goes, as the upward trip progresses, it covers less and less height, upward distance with each passing second. So you got to throw it very fast to get it to go up for 3 seconds. It's going to go 45 meters high. It's very similar to the stories we've been telling previously. It will cover most of that 45 meters in the first second and a bit. It'll go 25 meters in that first second. It'll go 15 in the second second, and only 5 in the third second, because it's running out of speed. So anyway, same story, just sort of changed a little around. Last detail to talk about it. What if the ball's not going straight up or straight down at all. It's coming at an angle. What's this like? You know, these things, those arcs. Well, beautifully enough, the motion of that arc can be divided into two pieces. A vertical piece, which is how high is it? Its altitude. And a horizontal piece, which is how far does it travel sort of downfield, sort of in a sports sense. And they're independent of each other. The up and down motion is a falling motion because it has a force involved in it, weight, which is straight down. So the up and down part of that motion is a falling and follows the rules we've just dealt with. The horizontal motion is that of a coasting object because the ball has no horizontal force acting on it. And so it doesn't speed up or slow down horizontally. So the motion then decomposes, or you can decompose it into a vertical motion, a horizontal motion. The vertical motion is everything I've talked about up until now, up and down. It goes slower and slower and slower, and then faster and faster and faster down. The horizontal motion is straight and steady. Well, it's not straight, it's just steady. It actually is straight. It doesn't turn around in the corner. And the result is you get these arc shapes. The arc, which it happens to be mathematically a parabola. That's nice. It's not worth pursuing why. But it goes up and comes back down. It's making steady progress horizontally while it's going up, rising to a peak, descending faster and faster. And what I want to show you here is, can I get this to go? Here we go. Who's this guy on the screen? Hey, there's me. Okay. I made an online version of this course, pieces of it, on Coursera. And so this is one of those videos. And I was over at the AFC filming these three guys who were shooting from half court, basket after basket. Man, were they good. It's just unbelievable. So I can't show you all their shots, but I'll show you one of their shots and me playing with it. Here. So let's see. We don't get any sound. How do we get the sound? Yeah. I've lost the sound, but that's okay. You know, technology, I love it. Okay, so this guy had shot this basket. There are the balls at equal time intervals going across here and swish. And what I want you to see is that vertically, the ball is rising to peak height, namely this, and descending. It's going slower and slower. It's covering less and less distance with every increment of time until it reaches peak height, and then it goes faster and faster downward. So it's falling vertically. It's following the rules. What's it doing horizontally? It's coasting. It's going steady speed all the way to the basket horizontally. There's a little bit of perspective here that sort of makes it look, this is farther away and at an angle, so it looks like these are getting closer, but it's steady and straight and true. So things thrown at angles travel in arcs. Just to finish these ideas off, if you want a ball, there are all these sports that want the ball to do certain things. If you want the ball to reach the other person as fast as possible, don't go up as much. Basically throw it essentially right at them. You'll have to accommodate for the falling process a little bit, so you have to throw it a little above horizontal. But that will give it the greatest speed toward them, given that you can only throw a ball or kick a ball so fast. If you want the ball to stay in the air longest, to not come down for a long time, you're a punter in football, you want the ball up there for 5 seconds. How are you going to do that? You kick it straight up. Because now you put all the speed you can summon into the upward motion. It goes up to, reaches peak height eventually and comes back down. If you want it to go the farthest, and this is the finally one that's, in the absence of air, you make a compromise. If you go horizontally with your throw or kick, it'll go very fast downfield, but it won't stay in the air very long because it's close to the ground. It's going to fall and it's going to hit the ground in a fraction of a second. If you go straight up, you'll keep it in the air a long time, but it's not going to make any progress downfield. Bad choice also. Go at 45 degrees. It's not very surprising that the geometric compromise between horizontal, which is fast downfield but doesn't stay in the air long, and vertical, which stays in the air long but doesn't go downfield fast, At 45 degrees, you get a good compromise between the two, and the ball goes the farthest in the absence of air resistance. All right, with that, I'll call it a day and look at ramps on Friday.